Welcome back to ECE 442-542. Your fifth homework assignment, the first one, post-exam 2, is due on Thursday, if you haven't already turned it in. And there are a couple of changes, as I said, as we get closer to the end of the semester. People are bumping my schedule all around. So for the next 2 Thursdays, office hours will not be at the 10:30 to 11:30, but they will be from 12:30 to 1:30 p.m. So if you're interested in seeing me during those time slots, please make sure that you catch that change. I won't be there at 10:30 at the normal time. As I said, homework 5 is due tomorrow. And if you're in 542, that project is now posted on D2L. And does everyone remember when that's due? The 3rd of May. I assigned it so I wouldn't forget it for that date. No, but it's the 3rd of May is when that one's due. Today what I want to do is get into a new topic. I already, and this is not an April Fool's joke, I actually recorded more information on yesterday, and that's now posted on D2L. That concerns finishing up that example that we started on the DC motor using the Ragazzini approach. And I want to make it clear that if you do not have unstable zero factors or unstable pole factors, those corresponding restrictions in the Ragazzini approach you don't have to worry about. If you're doing a problem and you have no unstable zeros in your original system, no unstable poles, then you don't have to worry about those two restrictions that pertain to unstable zeros and unstable poles in the method of Ragazzini. Hopefully that's clear. What I want to do today, though, is talk about a new controller technique, which is really, in a sense, less complex than the Ragazzini approach. But in the process of discussing the PID controllers, I'm going to go through sort of each piece individually, and as I progress through that, it'll be natural to just start talking about a root locus. And so we'll develop the root locus strategies, or a way to sketch root loci based on thinking through this, let's say today, the proportional control strategy, which is just one of the 3 pieces of a PID controller. And we'll look at limits on the gain, K, that influence stability. So now think of K as like a knob on an instrument, and you can adjust that knob, and maybe you can move that knob to 1/2 and then up to 5, and your system will still be stable. Or maybe you can adjust that knob from 1/2 all the way up to infinity, and your system is still stable. That's probably not going to be the case in most digital control systems. But now your knobs are going to have a proportional knob, an integral knob, and a derivative knob if we had a 3-term controller for the PID. Today we will probably only get into the proportional piece of that controller, and we'll start developing some root locus construction techniques, and they all hinge on this equation, 1 plus k g of z equaling 0. Everything is derived from that relationship, which really is the relationship that governs the closed-loop dynamics of your system. And we can break that into 2 pieces. A magnitude condition, if you solve this 1 plus kg of z equal to 0 for kg of z, hopefully you can see that kg of z is equal to -1. But -1 we can write as a in polar form as 1 at an angle of 180 degrees. But 180 degrees, we can get there either going 180 or -180, and we'll use the -180. Meaning -1 has a magnitude of 1 and an angle of 180. And those 2 conditions, we'll call them the magnitude condition and the phase condition, allow us to derive different rules for sketching the root locus. And the root locus is really just where in the complex z-plane do our closed loop poles have the possibility of living, or where can they lie in the complex z-plane. And where they exactly are will depend on what we choose for the gain in our system. I want to just quickly scroll through, literally, an overview of the PID controller, and then we'll go into the first piece, which is the P piece, the proportional controller. But you could think of a proportional controller as consisting of three separate little pieces, and they each operate on the air signal. The air signal is just the difference between the reference and the output. But based on that E, you could either have a proportional input term that's proportional to the air. You could have a input component that's an integral relationship of that air, and you could have another input piece that's proportional to the derivative of that air. And those three pieces each provide us with a little bit different flavor of how we're processing that air signal and influencing or adjusting the closed loop dynamics associated. And now you could think of this whole piece between E and, maybe I'm really anxious about this because this particular page on my OneNote kept dying when I was doing this, so I'm just going to start getting that circle of death. I'm going to try to get off of this page as quickly as possible, but we'll see. I'm nervous. But U is now made up of three pieces, but the transfer function between E and U is just this normal controller that we've been designing. It's different, but it will be a capital C of Z, just like we derived for the direct design approach via Ragazzini. It will give us a controller. Here's how to think about those three little pieces: the P piece, the I piece, and the D piece. Like I said, you don't want to pronounce this PID during an interview. You might text it as PID. You don't even have to put a period between those capitals. But if you do PID, you're saying proportional integral derivative. That's the shorthand for those three pieces. The proportional piece just scales the air. And what's that mean? Well, that just scales or adjusts the air signal at the present time. Let's say the present time is T sub 0. The integral component of the PID controller is doing just what it says. It's integrating the air signal from, let's say, minus infinity up to the present time. Maybe I should have called that T0, but I'm just using T, I guess, at the present time here. Meaning, what happens to that air signal between minus infinity to T? That's all the air in the past. This piece, the integral term, then works with the past air signal. We have a proportional term that works with the air right now. We have the integral term that works with what's happened in the past, and that's going to allow us to drive errors to 0. This is a good thing for steady state accuracy, our integral term. And the third term, the derivative term, this is now working on the derivative of the air, and the derivative of the air gives us a slope. If you think at the present time you have a slope associated with the air, and then you scale that, you're just sort of projecting into the future based on what the air has done in terms of its slope at the present time. The D piece is like an anticipatory piece of our controller. So now we have a present piece, P, a past piece, I, and a future piece, D. And those three pieces give us a pretty effective strategy for controlling a lot of systems. That's the idea behind a PID controller. Here's another picture of that concept, and here is where my system just kept crashing for whatever reason. Maybe it was not under control, but we're going to control it with the PID controller. This is the picture, the image. If you have a waveform that's your air, if we said T naught was right now, then the P piece of the PID controller is working with that air at the present time. The integral piece is working with the air that's already happened, and it's basically integrating the air signal between minus infinity, or whenever you turn it on, and now. And the derivative piece, the D piece, is working with basically how am I sloping at the present time, and I'm going to then project into the future or anticipate what's going to happen, and that will actually allow us to enhance the transient behavior. The I piece is steady state accuracy, the derivative piece is transient behavior. All right, now that we have all of that well understood, let's see if I can get to the page that maybe, oh, it'll probably die anyway too, but let's now, oh, and I need it to be bigger so that I can see this. Here's now proportional control discussion. This really is saying that we have our controller is just a gain. We're going to pick a gain K. And to get us on the same page as far as what's happening, here is our standard block diagram with unity output feedback. Here is our reference signal that we're applying, the Z transform of R, which is R of Z. Here is our output, Y of Z. Here is our plant, G of Z. Here is our input signal to the plant, but now we've agreed, oh, and here is our air signal. That's just the difference between the reference and the output. But right now, today, for the rest of this period, we are going to be focusing on restricting that controller to just be a gain, a K. And we want to think of that as a knob, and we want to say, okay, when we adjust that knob, what's the right setting for that knob? Is it at 12 o'clock? Is it at 2 o'clock? Is it a value of 1/4? Is it a value of 6? Is it a value of 30? What can we pick that K value to give us the behavior that we want in this closed loop setting or in this closed loop system? If we're interested in the closed loop behavior, what can we then create between R and Y? That was maybe a vague question. But what do we talk about in this class a lot of times? Transfer functions. We are interested in the closed loop transfer function between the reference signal R and the output Y. What's that in terms of what we have up here? And the T better just be a function of G and K, right? It better not include R and Y or E and U. The closed loop transfer function can only be a function, or should only be parameterized by the controller and the plant. We are interested then in the external transfer function, which is this transfer function between R and Y. So that T sub C of Z and it came back to me halfway through talking about this in earlier lectures, but when I've taught 441, that's in the fall, and what happens in the fall? Football. So we had to do cheers, and we were we had class on Friday morning, so we had to get ready for the game on Saturday. So we would do cheers. And one of the cheers that we had was, how do we find the closed loop transfer function? So you would give me a G, and G was actually whatever was in that forward path. In this case, it's KG. Okay, so we're KG. KG, that's the forward path, and then I would say give me an H, and that would be what was in the feedback path, but then it would be the closed loop transfer function is G over 1 plus GH, and that was our cheer. So if we do that here, the forward path we have upstairs over 1 plus the forward path times the feedback path. And the feedback path here is 1. Meaning, our closed loop transfer function, y over r, is just the cheer, k g of z, over 1 plus kg of z. And you could derive that. We've derived that many times, but now that you've seen it derived, you should just be able to reproduce it instantly when I say, okay, what's the transfer function for this block diagram between r and y? What governs the closed loop behavior dynamics of the closed loop system in this transfer function? Can you point to anything here that's going to influence the dynamic behavior of that system? I'm waiting. I'm just kind of writing to buy time to give you time to think. But we have the dynamics of the closed loop system. Are governed by what? And this closed loop transfer function is really a ratio of ratios, isn't it? In general, g of z is a ratio of polynomials. So we have a ratio up top, and we have that divided by a ratio downstairs. So this is a ratio of ratios. When you see 1 plus kg of z, you actually have numerators and denominators in that expression. But the dynamics, I like to say, of this transfer function are influenced by the denominator expression, which is just 1 plus kg of z. So the dynamics are going to be governed by the denominator, let me just say by 1 plus kg of z. We set that equal to 0 to find the roots that would then give us the modes of that dynamics. Let's talk about this via examples so that you have something to sort of keep track of or think about. Let me call this example 1, and let's say that the transfer function g of z we have determined to be 1 over z minus 2. That's our plant. And we want to know, what can we do with that plant using proportional control? What can be done for this closed loop system with proportional control? Can you now give me the closed loop transfer function if I've given you g of z and you know what the controller is? The controller is a proportional controller, so it's just a gain k. C of z is k. That means that we now have this t sub c of z is just the forward transfer function k g of z over 1 plus k g of z, which is our cheer, kg over 1 plus kg with unity output feedback. And if we replace g with what we said we were looking at in this example, yes? You sure can. Just don't turn it on. You're being recorded. We've got a video. It's monitoring the class. As long as you know, I wondered who was going to come and get that. Thank you. You too. Thank you for waking up the class. If you were going to fall asleep, I was going to turn that blower on and see what happened. The people at home would wonder what noise was being produced. I thought maybe they'd spilled something. Maybe they cleaned the carpet, and so they were drying the carpet. That's what I assumed. I guess he didn't take my backpack, did he? Has my sandwich, my dinner in it, so I need to make sure he's... All right, where were we? We have kg of z over 1 plus kg of z, which is just that. And now if we, so I'll do this, well, everybody sees that I'm going to have the same denominator in the numerator and denominator, right? So I have a denominator of a denominator, and I have a denominator in the numerator. I'm going to cancel those, which is the z minus 2 factor. But that leaves me downstairs, that z minus 2, I need to have that 1 become a z minus 2 over a z minus 2, so that I now end up with k over the quantity z minus 2 plus k. Is everybody okay with that? Now I have just a ratio of polynomials for my closed loop transfer function. And that 1 plus kg of z really has reduced down to the numerator expression in 1 plus kg of z. And that's the denominator, z minus 2 plus k. And that particular polynomial, which in this case is just first order, but that polynomial is what influences the dynamics of our system. So now let's look at that. Let's say, okay, our closed loop dynamics, just to reiterate, I might say that that is governed by many different things, but it's all sort of the same. It's governed by 1 plus k g of z, or it's governed by the roots of 1 plus k g of z equals 0. Those are the values of z that cause that to vanish, which are really going to be in the numerator of that expression. So I could say, or those are the numerator polynomial of 1 plus k g of z when that's equal to 0. And in this case, for our example, that's what we have. We're setting the numerator of 1 plus kg of z equal to 0, and the values of z that cause that to vanish are the modes of our system, and those govern our dynamics. Are we okay with that? So the dynamic behavior is influenced by the denominator of our closed loop transfer function, z minus 2 plus k, and in fact, that's just the numerator of 1 plus k over z minus 2, or 1 plus kg of z. That influences our dynamics. And what we want to do with this particular expression is to actually adjust k to give us what we want. K, remember, is our knob. That's our proportional gain amount. So we want to adjust k to locate the closed loop poles, and in this case it's just a pole, so let me just say the closed loop pole in this particular problem at an acceptable location. Meaning, if we take this expression right here and we solve that for z, we are going to end up with z is equal to 2 minus k. And we now have the ability, we'll just look at k positive when we rotate that dial. K starts at 0, and we're going to go all the way up to a potential infinity. What happens if I now said, can you sketch in the z-plane the locus of points that z maps out as we adjust k from 0 to infinity? And that will be our root locus for this particular system. Meaning, if I start that dial at 0, where's my root locus going to begin? At what value of z? 2. And that's actually where if I look back here, my open loop pole was where? At 2. So my root locus is going to begin on my open loop poles of g of z. If I come back here, I now say, okay, here is my point 2, and let's say this is now my open loop pole in the z-plane. And now I want to shade in red the root locus associated with this system. What values of z in the entire two-dimensional plane represent allowable closed-loop poles? And those are going to be created by adjusting k from 0 up to infinity. And you just told me that I'm starting right here at 2 when k is equal to 0. As I increase k, where am I going to move in the z in the z-plane? Towards the origin, aren't I? Left, because I'm going to become more negative as I increase k through the positive values. So I hope it's clear that k, as I increase it, and those arrows show the direction that I will move as k increases from 0 to infinity. And this represents then the locus, or yeah, let me just call it the locus of potential, getting tired so I'm texting, closed loop poles. Meaning, these are the only values that I could have for closed loop poles, is where that red line is. And to get a particular design, I have to specify a specific value of k. And probably the first thing I want to do is find a k that stabilizes the system. Is my open loop system stable? Is my g of z an acceptable response in terms of behavior? No, is it? I'm over at z equal 2, and that's outside the unit circle. You need to be thinking or focusing on the unit circle, and you want this red line or red lines. We may have multiple branches when we have a higher order system than a first order. We want all of these branches to be inside the unit circle simultaneously for our closed loop system to be stable. Let's design some stabilizing controllers. We need to identify that point right there at 1, and we would, maybe I'm getting ahead of myself, we're also interested in that point at -1. As long as we live between 1 and -1, we're stable. Is that okay? We're inside the unit circle. I haven't drawn it because I can't draw a circle. But you can visualize a circle. As long as your red line is in that circle, then you're stable. Let's look at some possibilities. And a lot of times what you're doing is actually setting up desired polynomials, and that's what you're doing on homework 5. You're finding desired polynomials to meet those specifications, those performance specifications. But here, let's just look at a possibility. One possibility for K, again, the closed loop characteristic polynomial is given by that. That's our denominator as a function of K. Maybe somebody says, you know what, I want my desired closed loop polynomial to look like z minus 1/2. Here is our desired polynomial. And this is just our closed loop polynomial as a function of K. And again, we're adjusting K between 0 and infinity, and we're trying to find the sweet spot on that dial, the right values of K that stabilize the system. And one point that I'm suggesting might be okay is if we had a denominator that looked like z minus 1/2. Where's the closed loop pole for that polynomial? 1/2. It's the value of z that causes that to vanish. And that's a pretty good place, right? It's on the real side in the z-plane. It's at z equal to 1/2. And so my closed loop pole, if I can find a K that makes this left-hand side look like the right-hand side, I'm in a good position. And that's all I have to do is equate the coefficients. The z coefficients are the same, so those go away, or I can just subtract z from both sides. It's however you want to think of it. But if this was a higher order polynomial, if the desired polynomial was 6th order, or on your exam if it was 12th order, you would then have to worry about all these coefficients, these 12 coefficients, plug those, well, solve those, invert a 12 by 12 matrix, and give me the answer. Took off my glasses so I can't see your smiles for wanting to do that particular problem. So in general, what you're doing to solve that, here it's pretty obvious, but in general, you want to equate coefficients. And in this case, you're equating the z to the 0 coefficients on the left and on the right, the constants you're equating, meaning you're letting minus 2 plus k equal minus 1/2. Or add 2 to both sides, and k now we've dialed it up to 3/2, and 3/2 will get us inside the unit circle to a location of z equal to 1/2. If that's the k value, what's going to be the resulting closed loop transfer function? You already have it in terms of k, right? And you've just picked k to give you a specific denominator. Your denominator is z minus 1/2 in t sub c. If you plug in k equal to 3/2, you're going to end up with z minus 1/2 downstairs. And upstairs is k. That's 3/2. So your closed loop polynomial or closed loop transfer function is now simply 3/2 z minus 1/2. This is our closed loop system. And what can you tell me about that closed loop system? Anything interesting? It's stable, isn't it? Because the denominator, all the roots of the denominator are inside the unit circle. We only have one root, but it's inside the unit circle. And what do we know about C of z that caused that? How elaborate was our controller? Wasn't it just k equal to 3/2? Is this a little easier to think about than the C of z's you were getting via Ragazzini? This is just a proportional controller. You're just cranking up the gain in that proportionality block, in the controller block, to stabilize your system. You didn't have to go through all this stuff that you were doing with Ragazzini. Is this controller going to cancel any unstable poles and zeros in our original system? No, it has no factors in it that might cancel. You had an unstable pole. You definitely don't want to be canceling that, do you? So now you're bringing that pole inside the unit circle without canceling it with feedback. You're pulling it in with the appropriate adjustment of the gain. That's what you're doing with this proportional controller. So there's no unstable pole or zero cancellations with C of Z equal to K equal to 3/2. That looks like 33/2, so I better correct that. 3/2. All right, before you start resting and thinking, oh boy, this is easy, what could possibly happen that your boss is going to complain about with that controller? I know, your boss is nice. They never control, or never control. They never complain or get upset. What might you be interested in? You now have a system that's under control. It's stable. What are you going to do with that system? If it represented a Segway, an inverted pendulum, you might want to drive that, right? You might want to give it a command. You might say, go, move. Probably don't want it to just sit there. That's the whole point, right? You're trying to control a system. So if we put in a reference, maybe just a constant input, what's going to happen? What's going to influence the behavior? Okay, I'm trying to bait you to try to get you to think about what you might be interested in. What's the DC gain of that system with this controller? So what's the DC gain of T sub C of Z? And why am I interested in that? Because if I apply a constant, the DC gain is going to be how I scale that constant. And if this is a nice system, then what I put in is what I'm going to get out. If I put in 10 degrees, I want to get 10 degrees out, maybe. And the DC gain will tell me what's going to happen. How do I find the DC gain of this closed loop transfer function? I evaluate it at z equal 1, don't I? So this is now going to be, upstairs we had a 3/2, and downstairs we have a 1 minus 1/2. We have a DC gain of 3. Is that okay? I have a thumbs up, I have a no, I have somebody over here flipping a coin. And I have no clue what's on that coin. Could have a 0 or a pole or a yes or a no, a D or an N, numerator, denominator. Let's look at the steady state error so that we can make an informed judgment call. And on your homework, number 5, a lot of these problems maybe aren't completely specified, and it's up to you, the budding engineer, to pick something, to show your expertise in how to design something. All right, so here we have a steady state error, or do we? Is it going to be 0 to a unit step? If I apply a unit step, what's the reference signal look like a long time into the future? What's R sub infinity? That's my step at n getting really, really big. Unit step. Hint, it's 1, isn't it? So R sub infinity is 1. What's the output? Is it well behaved? What determines the behavior of our output? Before we get to infinity, are we going to reach a steady state? Okay, yes. I heard some yes. It came from the blower, or the corner where the blower was. I missed that blower, if you couldn't tell. I really did want to plug that in and see what would happen. Probably blow a fuse is what I would do. I'm an electrical engineer. Figure it out. All right. Where were we? Oh, well behaved. Somebody said, or is that the question? I forget what I asked now. How do we determine whether this system is well behaved? Do we have a stable system? And you've already designed it to be stable, so it is well behaved. We will reach a steady state, but where are we going to reach? It's going to be the constant times our DC gain, isn't it? That's where we're going to end up. So this is going to be our DC gain of 3 times our final value, 1. Our steady state output will be 3. So now what's our error at infinity? If we just go back to the block diagram, that was R minus Y, wasn't it? That was the output of our summing junction. This is now 1 minus 3, and we have now a magnitude of our error of 2, don't we? And we only put in a 1. We get out a 3. That's what the DC gain gave us. But our system's well behaved. At least it's stable. We have gained something. Before it was unstable, wasn't it? So now, in terms of, this is a pretty big error, but if you just were thinking about this in terms of a time response, you were looking for something to go there. That was our reference command. And what happened? What's Y going to look like? How is it going to approach its final value? Where's your pole? 1/2. Is it going to oscillate around your final value? No, because it doesn't have any imaginary pieces, does it? It's real. So it's just going to be an exponential. It's a first order exponential response. I'm not going to draw it as a dashed line, but I'm just going to say it's going to look, whoa. You know why I was doing that, right? Because I'm supposed to be getting to 3. So I have to give, oh man, give myself some. That's why I failed art class. Why do you think I became an engineer? It wasn't, are you good in math and science? Are you bad in art? Yeah, then you're an engineer. No, a lot of engineers are really good at art, right? It's just me. Where were we? Oh, we were trying to go to our steady state. And this is now our error signal. That's our error. And maybe that's not what we want. Here is time. And we have this first order response. You won't see an RC circuit with that ugly kink in it. It will be a nice, smooth, exponential behavior. That's just my drawing. But you may not like this. A proportional controller may not give you the behavior you want. Maybe you want to lock on to that 1. So a proportional controller you may need better than that, more than that. But at least you stabilize the system with a pretty stable controller, just a gain. But let's just sort of conclude that little piece by saying we may need a different controller structure. I mean, if that gain of K solved all of our problems, you wouldn't be sitting in this classroom, right? Because they could just pull anybody off the street and say, build a controller. Oh, that's just a gain. And they'll just adjust it and then they'll leave. Well, they'll probably take some pay for that adjustment, but then they'll leave. But you want to be gainfully employed for longer than that, right? So you're kind of happy to see that maybe you need more than just a gain controller in certain cases. But at least you know how to stabilize the system. In this case, our proportional controller or let's say proportional control may not produce an acceptable steady state error. So you might have to buy a vowel. It's about the time for Vanna, isn't it? May I buy an I? You might need a PI controller, not just the P. Is that okay? What is that? Oh, that's Wheel of Fortune, isn't it? Is that right? Yeah. So you may need a PI controller, not a P controller, to give you zero steady state error. And that makes your system a little bit more challenging. But let's just move on. Let's just see what we can learn just by this simple first example with a gain controller. We've just picked one value for K. What if we increased K? So that's sort of telling us maybe we need to worry about more than just a P controller. But one could increase K to yield, oh boy, you're going to like this, right? A deadbeat response. Now, our closed loop polynomial is z minus 2 plus K. What does that need to look like if I want a deadbeat response? It needs to just look like z, doesn't it? I want in my denominator a pole right at the origin to produce a deadbeat response. So here I'm equating polynomials. Here is my closed loop polynomial. I'm setting that equal to a desired polynomial. In this case, a desired polynomial that produces a deadbeat response. If this is the case, now I can see by equating coefficients that I want minus 2 plus K to be 0. Or I need to crank up K a little bit beyond 3/2. I now need to crank it up to 2 to get my pole to move closer or further in the unit circle and become lodged right at z equals 0. What's your closed loop transfer function now? For this choice of gain K. We've now cranked it from 1.5 up to 2. And what's T sub C of Z look like? It's still K over the desired polynomial. And K is 2. And you picked K to be 2, and that's going to cancel your minus 2, so you end up with 2 over Z. This is now your desired transfer function for that increased value of K. So we went from 1.5, which was stable, to 2, which was stable. Can we just keep going with K? Bless you. Is there a limiting value of K for stability? This is just begging to be an exam question or maybe a homework problem. But you guys attended today's class, so you might actually get this on the exam. Here's the z-plane. You better get this if I gave you this gift, right? First order system, and you're controlling it with a proportional controller, and I'm asking you for the range of K for stability. And you might want to verify your answer by sketching the root locus in a z-plane. You may not want to just give me an answer. I might say, where did that come from? You might say, well, here is my thought process. The open loop pole was at 2, wasn't it? And the only location for my closed loop poles, both possibly unstable and stable, are all the values on the real line to the left or more negative than 2. So as I crank up K from 0 to infinity, I can map out all of those possibilities for my closed loop poles. I want to now find what are the K values that will stabilize that system. This is actually the root locus. If I ask you to sketch the root locus for that g of z, which was 1 over z minus 2, this would be it. That would be your root locus. But now, based on this, can you tell me what you need to be worried about in terms of finding this range of K for stability? We need to have this, we need to identify the values of K that keep us inside the unit circle. So here's a 1, and there's a minus 1. And if I say that this is now, our closed loop pole is a triangle now when it hits that point, and maybe it's a square here, which one do I get to first? The triangle or the square as I crank up K? So this is now representing my lower limit on K, and this is now my upper limit on K. The lower limit is what? Well, that's when z minus 2 plus K is equal to z minus 1, right? This is my desired polynomial when I'm right at the triangle. And now I can just equate coefficients. And if I solve that for K, I end up with minus 1 plus 2. Or if I cranked up K to 1, I would be right on the stability boundary. At the lower, or I'm sorry, at the upper limit of K, which is what I indicated with the square, then this closed loop polynomial that's a function of K needs to be equal to what polynomial? That's now equal to z plus 1, and now this is 3. So if I ask you on the exam, give me the range of K for stability of this unstable system, you have to at least crank up the gain a little bit to get yourself inside the poles inside the unit circle. The range of K for stability in this particular system, K needs to live between 1 and 3. Is that okay? That's the answer that you would give or provide if somebody said, what's the range of K for stability for this unstable system? And you would then, your only design freedom is to select K between 1 and 3 to produce whatever it is that you want to produce. But your system will be stable between those limits. Is that clear? And this may not give you the steady state accuracy that you want. So you may have to go with a little bit more elaborate or complicated. You might have to buy a valve, right? You might need a PI controller. You may have to introduce the integral piece. You may not be able to get what you want with the proportional piece. Let me just say what a standard root locus is, and then we'll move on to another example. We've sketched a root locus. That's just that red line right there, and hopefully none of you will red line when you're sketching a root locus, but you'll at least be able to sketch a root locus, right? I hope. It's usually a little bit more interesting than that. We have lines, we have more than one branch in general, but a standard root locus is given by the roots of 1 plus k g of z equal to 0. As we adjust k, or as k is increased, from 0 up to infinity. So if I don't say anything otherwise, a generic root locus is for positive or non-negative values of k. I won't be trying to trick you necessarily, but sometimes in a system you might actually have to use a negative gain to stabilize the system. But generally, we refer to a root locus when we're letting k go from 0 to infinity. And I think if you've taken an earlier controls class, you've surely seen this, a root locus. And it's actually the rules for a discrete z-plane root locus are the same as the S-domain rules. It's just now you're interpreting stability based on the unit circle and not the entire left half S-plane. That's the difference. Let's look at another example. Example 2. Suppose that now you're given g of z equaling 1 over z minus 3 halves. Is that system open loop stable? And if you can't read my writing, you're going to go, I don't know, I can't read your writing. So let me clean that up a little bit. Is that system open loop stable? No, so you're going to have to stabilize it. Now we might ask, is there a stabilizing value, or maybe even a range of stabilizing values for k? What are we thinking about when we are talking about, and a lot of times it helps to just remind yourself what we're dealing with, and for that reason you might actually want to just sketch the block diagram to remind yourself what we're working with. Here's our reference signal. Here is our controller, and we're just asking, can we get by with a gain, k? Here is our plant, g of z. And we are going to feed that output back without a gain. It's unity out, I mean, it's a gain of 1. It's unity output feedback. What's the closed loop transfer function? In terms of k and g. This is our cheer, isn't it? So this is now kg over 1 plus kg. So if you want extra credit, you might get 1/4 of a point out of 50 if you put that down. Kg over 1 plus kg. We are looking for now, for stability, what do we want? We are asking for the range of k for all roots of 1 plus k g of z equal to 0 to lie inside the unit circle. How many roots are we looking at? Our plant, our open loop system, is giving us 2. Is our controller giving us any poles? No, because it's proportional. When we start getting a more complicated controller, then we may be upping how many poles we have in our closed loop system. Here we only have 2, all determined by our original plant because we are just using a proportional gain k. Let's now look at the root locus associated with this particular system, g of z. And that's going to then be determined from that equation. That's our governing equation. We want to know what values of z satisfy this equation as k varies from 0 to infinity. That's going to be our root locus. But if we look at this, I hope it's clear that if we subtract 1 from both sides, we get kg of z equal to minus 1. But minus 1 we can write as 1 at an angle of minus 180 degrees. Which means, because kg of z in general is a complex number, isn't it? G of z is a transfer function, and z can be complex. So kg of z is a complex number, and we need that in order for it to satisfy that denominator polynomial set equal to 0. It has to be 1 at minus 180. All the points z that satisfy that equation will be on our root locus, on this set of points in the z-plane that will be possible closed-loop poles. Now, if we restrict k to be non-negative, then the angle of, so now we're interested in the magnitude of kg of z, that's going to be 1, and the angle of kg of z is going to be minus 180. But if we're interested in the angle of kg of z, and k is positive, k is not going to adjust the angle, is it? And we need that angle of g to be minus 180 degrees. Good thing I didn't turn on that blower and stir up more allergens, huh? Maybe that's why they did the carpet. Never mind. So now we have the angle of g of z being equal to minus 180. That being said, how do we sketch our root locus? Well, the first thing that you do is you draw your z-plane, and you place on that z-plane drawing your open loop poles and zeros. Your poles will be x's, and your zeros will be open circles. Where am I going to sketch x's and o's? So now we see, that's why in the fall we were drawing x's and o's, and they represented football teams going different directions. Now I guess we could have basketball players, x's and o's. We now have x's and o's. The x's are the poles. The zeros are our the o's are our zeros. Where do we put x's? Do we have any o's in g of z? Any open loop zeros? No finite zeros, do we? We have 2 poles, one at the origin and one at 3/2, and so we can sketch those by simply putting an x there and an x there. Now what we want to do is say, are there any points on the real line in this complex z-plane that belong to the root locus? Can we shade any of these segments? So we have three segments of the real line. Now, because we've split it up into three pieces, we have a segment from 3/2 to plus infinity. We have a segment of the real line between 0 and 3/2. Sorry for those of you at home, you're not getting the full benefit of this, but you can just imagine me with my arms outstretched, leaning up against the wall. But then the third segment is from 0 to minus infinity. Are any of those three segments a part of the root locus? And what do we know? Well, we know if they're on the root locus, the angle of G has to equal minus 180. So let's just look at, so that this becomes very clear, let's just hypothetically produce three different points in the three different segments of our real line. Here's one, there's another, and let's make a third. There's a cloud, okay? That's a cloud. We have a triangle, a square, and a cloud. Those belong to the three distinct segments of our real axis. And we want to know, is the triangle going to be shaded red? Is the square going to be shaded red? Is the cloud segment going to be shaded red? Which of these become shaded? So now we want to know which points, and really the points define the whole segment, which points, triangle, square, or cloud, kind of looks like a ghost, I guess, which points lie on the root locus? So let's look at the triangle. And what we're saying is what's the angle of this transfer function g of z when z is out there at the triangle? So we're now saying, what was our transfer function? That was 1 over z times z minus 3/2. And we want to know what's the angle of that combination of zeros and poles when we evaluate those factors at the triangle. And what kind of an angle do they produce? Or we could really get crazy. We have the angle of the numerator, and we have the angle of the denominator, all evaluated at that triangle. Or we can break all of these pieces up into their own factors that contribute an angle. And the angles, I hope it's going to be clear that the angle is defined by measuring the angle relative to the positive real line or horizontal line from the point in question. Meaning, if I want to know what angle do I look at, so now I sort of have this shark mouth or bite. I want to know what's the angle between my jaws. If I now look here, my lower jaw is the positive real line, and my upper jaw is at the triangle. What's the angle produced by 3/2? Is there any angle between those jaws? It's 0, isn't it? But here, I'm getting ahead of myself, maybe. We now have the angle due to 1. We have the angle due to z, that's the pole at the origin, and we have an angle due to the pole at 3/2, which is associated with this factor z minus 3/2. Well, that now contributes or gives me an angle of 1. And what do I do with angles that are in the denominator, downstairs? And when I'm computing the entire angle for the whole expression. I have angles from my numerator terms, and my numerator term was just a constant. So I'm looking at the angle of 1. If I had a factor up there, I'd look at the factor, let's say z plus 1/2, but I don't. I just have the angle of 1. Then the denominator angles subtract, don't they? If you think of these as complex numbers in polar form, if you combined all of those pieces, your denominators are subtracted in terms of their angles. Meaning I now have the numerator angles minus the angles of my denominator factors. And you've already told me what this angle was on the far right. But what's the angle of 1? If I go up here and I say, oh, here's actually 1, but really I'm looking at 1 as a number, what's its angle? 1 at 0, isn't it? So its angle is 0 degrees. This angle of 1 gives me 0 degrees. What's the angle from this point, z equals 0, out to that triangle? It's 0, isn't it? So now I'm subtracting 0. And what's the angle from here to that triangle? 0. So I add those up. That's going to be hard to do. And what am I checking? If it was on the root locus, these were supposed to be summing up to minus 180. And it's not, is it? 0 is not minus 180. So that, all of these points here in that line segment are not belonging to the root locus because they all have an angle of 0 degrees. Is that clear? Any point there in that shaded blue region would produce the same angle. So now I have that all the points, so now what I can say is therefore points to the right of z equal 3/2 do not live on the root locus. What about the delta? I'm sorry, the square. Can't even tell you my shapes. Now we're looking at g of z when z is the square. We have the same terms. We have 1, that's the numerator pieces, minus the denominator pieces, evaluated now at a different location, which is the square. So if we go back here, and now we look at the angle from each of these points, well, 1 still has an angle of 0, doesn't it? But now, what's the angle from the origin, z equals 0, or z, to the square? That's 0, isn't it? What's the angle from 3/2, the pole, the open loop pole at 3/2, to the square? Shouldn't have done that. It's 180, isn't it? Or minus 180. So now well, it's 180. Let's just say that this angle, looking back there, that we had to look through 180 degrees. This now says I have 0 degrees minus 0 degrees minus 180 degrees, which is minus 180 degrees. That says that this square, or the points between z equals 0 and z equal 3/2 do live on the root locus. They all give us an angle of minus 180. So these all lie on the root locus. Bless you. Where was I? So now I have this. Oh, I knew I shouldn't be scratching over it too much. But that segment now between 0 and 3/2 is a part of the root locus. What about this cloud? Is that segment on the root locus? It now has 180 from the pole at 3/2. It has another 180 from the pole at 0, and it has nothing from 1. So I add up 2 minus 180s, and I get 360. That's not equal to minus 180, is it? So this segment from 0 to minus infinity does not belong on the real root locus. My root locus now comes, let me erase this. My root locus now is living between, on the real line, 0 and 3/2. Now what happens? As I crank up the gain k, these two branches, I now have two branches, one starts at 3/2, one starts at 0. They are going to meet. And they can't just stop there. They have to go somewhere. We're going to learn that those now go off at a specific angle or in specific directions. They go off at plus and minus 90 degrees, and now that's our root locus for that combination of poles. Meaning, can you see where you might have stability or not? If you're now concerned with stability, whoops, I wanted that to be black. Now we're interested in we would want to know what's happening here and there. Between those points of the gain k, that would give us a stable range of k. And we'll have to pick up at that point when we talk again, unless I want to do this again by myself and you can watch it. Maybe I'll do that. So stay tuned. Thank you.